So this PT video is about the greenhouse effect and global warming. And in order to understand this properly, we need first of all to look at the effect of the temperature of an object on its emission. So two key ideas here. The first is that if we had a hotter object, it gives out more radiation at all frequencies than cooler objects. So right across the electromagnetic spectrum, a hotter object will give out more radiation wherever we compare it than a cooler one. And the second thing is the peak of the emission spectrum. So that's the frequency at which it gives out the most radiation shifts to higher and higher frequencies as the object gets hotter. So why does that matter for us? Well, the two objects we're interested in for explaining the greenhouse effect are the Sun and the Earth. So let's have a look then. The horizontal axis on this is frequency, which matches the spectrum we've put over the top here, and the vertical axis is intensity, which is basically how much energy is coming off every second at the surface of these objects. So what the Sun looks like then is it has a range of wavelengths given out. In fact, it gives all across the spectrum, just very tiny amounts down in the radio and in the gamma. But the peak of its emission is somewhere in the middle of the visible part of the spectrum, because the Sun has a surface temperature of about 6,000 degrees centigrade. If we look at the Earth, which has an average temperature of 14 degrees, it emits a lot less, and the peak of its emission, because it's a lower temperature, is at lower frequency in the infrared part of the spectrum. And in fact, we've had to magnify the curve for the Earth by about a factor of 1,000,000 on the intensity axis to even be able to see it on this scale on the diagram. Because obviously, as we've said originally, it should everywhere be underneath the curve for the Sun because it's cooler. So, in summary then, the basic takeaway from this is that the Sun emits mainly in the visible part of the spectrum because it has a high surface temperature, and the Earth emits mainly in the infrared as it has a much lower surface temperature. Okay, so what we need to do now is apply that to a model of the Sun and the Earth, looking at the idea of radiation travelling from the Sun to the Earth, being absorbed and then re-emitted. Okay. So obviously this diagram is not to scale. We've kept the Earth large because we're mainly interested in the processes going on in the atmosphere, so we can actually fit them on the diagram. So the first thing that happens then is the Sun emits photons, and as we said, mainly in the visible part of the spectrum. Those are transmitted through space, and when they reach the surface of the Earth, they are absorbed by the Earth's surface, warming it up. We're going to look at this without the atmosphere first to simplify, and then see what happens when we put the Earth's atmosphere in. So without the atmosphere, there's nothing to do anything to those photons. They come straight in, absorbed by the surface, and warm it up. And then what we've said is that the Earth emits mainly in the infrared part of the spectrum because it's cooler, and there are the infrared, longer wavelength photons emitting into space. Now actually, in reality, of course, because the infrared photons are much lower energy than the visible ones, there will actually be many more infrared photons emitted by the Earth than visible photons absorbed by it. But again, for the simplicity of the diagram, we're going to keep it to a few infrared photons to avoid crowding it. Okay, so that process of emission actually cools the Earth down, and then there's a balance established where the emitted radiation is completely equal in energy to the absorbed radiation, and the temperature stabilizes. So if we put the atmosphere in now, that has a couple of effects. It does very little, in fact, to the incoming radiation, because as we know, the atmosphere is mostly transparent to visible light because we can see through it, and most of the Sun's light is in the visible part of the spectrum. Yes, things like the ozone layer have a small effect on the ultraviolet, but the ozone layer is not really important for global warming, and you shouldn't be mentioning it in your discussion of greenhouse effect and global warming, okay? Because most of the Sun's light is in the visible. Okay, so that's the first effect, very little on the incoming radiation, but it does have much more of an effect on the outgoing infrared, because certain gases in the atmosphere, carbon dioxide, water vapour, methane, absorb quite strongly in the infrared. So they absorb the infrared that's being emitted from the Earth's surface, and then they kind of re-emit it again, and that basically traps some of the infrared radiation within the Earth's atmosphere. And this greenhouse effect is actually a good thing, because without it, the surface temperature of the Earth would be much lower, and it probably wouldn't have liquid water because it would be below the freezing point, and that makes it much more difficult for life to have come to exist in the first place, according to what we currently understand about how life will need liquid water. So the greenhouse effect on its own is not a bad thing. Without it, we might not exist. So what's the difference then between the greenhouse effect and global warming? Well, essentially global warming is when we have too much of the greenhouse effect. So things that human beings have done, for example, have massively increased the levels of carbon dioxide in the atmosphere. Burning fossil fuels, deforestation, because there's no photosynthesis going on, or less photosynthesis going on, I should say, has raised the levels of CO2. So what effect does that have? Well, as we've said before, the Earth's temperature is stable because the incoming and outgoing radiation are kind of balanced. But if we mess about with the atmosphere, then we trap more infrared. So we increased level of greenhouse gases cause more infrared to be trapped. So you can see that not escaping into space. And what that will do is it will raise the temperature of the Earth. Now, as we've said, if the temperature gets hotter, then that means more emission of radiation. So eventually, as the Earth warms up, it will start emitting more infrared, and that will re-establish the balance. The incoming radiation and the outgoing radiation balanced in terms of energy transfer. But of course this is now happening at a much higher temperature, so the overall effect of this is to raise the temperature of the Earth so that it can re-establish this balance. And that is global warming. It's basically too much of the greenhouse effect. Okay, and the last thing you need to really understand is the consequences of global warming, and there are many of them, some of which probably are unpredictable, but main ones: climate change. So that can mean increased or decreased temperatures. Remember, global warming is an increase in the average temperature of the Earth, so there are some regions that might get cooler as a result of global warming, rather bizarrely. More extreme weather events, so hurricanes, tornadoes, things like that, more likely to occur because there's more energy being put into the atmosphere. Melting of polar ice caps, obviously a very common consequence quoted for global warming, and that tends, of course, to lead with the increasing sea levels, not just due to the ice cap melting, but also the expansion of the sea, leading to flooding of low-lying areas. Increase in extinction rate because of climate change and other things, meaning species can't adapt necessarily rapidly enough to changing conditions, and so they may go extinct. And crop failures is another big one, because obviously similar to extinction, a crop might not survive if the environment changes too much in the area where it's grown. Okay, so that's how global warming works, the difference between global warming and the greenhouse effect, and some consequences of global warming.